The objective of this lab was to study the notion of contact force. Additionally, we studied the expression of normal force an incline exerts on a block, as well as we measured the coefficient of kinetic friction, the coefficient of static friction, and we used a force sensor, a photo gate, and passcode to analyze our data and to collect our measurements.
In this lab, we had 3 different assumptions, and based on these, assuming that they're all met, we found that the only force was long-range acting is due to gravity. So the contact force split into 2 parts. We had a normal force, which was perpendicular, and then we had a static force, which was tangential to the surface. And for a block of mass, on a normal force is equal to the perpendicular component of the weight, since there is no acceleration on the surface. So that's why you can see that normal is equal to mass times cosine theta. Normal force is in newtons, mass is in kilograms, and gravity is constant at 9.966 meters per second squared in Collegedale. This shows that the surface adjusts to apply exactly enough force to keep it. The frictional force is the tangential component of the contact force and opposes relative motion. If the block is stationary, then static friction values from 0 to a maximum. So we measured the maximum value by moving that piece of wood. As you can see, this block started moving using the equation f of x is equal to mass times gravity times sine of theta max. Coefficients are dimensionless ratios, and they describe sort of like how grippy the surfaces are. So the static friction is always equal to static friction because it takes more force to initiate motion than to maintain it. And application of the force decomposition on an incline expression for the coefficient of static friction when the block is just about to slip. At the threshold of motion, the downhole component of weight, like friction, so that this is where the mass times gravity times sine of theta is equal to the coefficient of static friction times mass times. And using Sakatoa, we can simplify this equation to the coefficient of static friction is equal to tangent. And this relationship shows us that the mass of the block does not affect the coefficient, but rather that it's the angle at which the block begins to slide. So Forkant law provides a connection between friction and motion. When a block is pulled apart at a constant velocity on the horizontal surface, 0, so the applied force equals a kinetic frictional force. So this is where you can see here that the force of the pull isn't kinetic times K mass times gravity. And then here the magnitude is shown as magnitude of the normal force. If, however, the block is given an initial push and is then allowed to slow to rest, entirely caused by kinetic friction. So it's not going to keep going on forever, as you would assume, because there is a friction that's stopping it. So the acceleration can be measured when we plot that velocity squared by the distance. And then because mass times gravity, this allows kinetic friction to be attained through the constant times acceleration. So we compared this experimental or this calculated kinetic friction to the experimental kinetic friction that we have activity 3.
With the first activity, we want to deepen our understanding on contact forces by examining how the normal force acting on a stationary object with an inclined plane depends on the angle of inclination. For activity 2, we compare 2 methods of measuring the coefficient of static friction, the horizontal pulling method and the angle of incline. And that is the way we verify that it is independent of the mass of the block. Activity 3, we want to examine how kinetic friction influences the motion of an object after sliding begins by applying Newton's laws to situations involving constant velocity and constant acceleration, and see the proportional relationship between kinetic friction and the normal force acting on the object.
In activity 1, we're recording the normal force over 5 different angles. We can measure these different angles with the goniometer. First, we want to take our force sensor, we want to calibrate it using the pulleys and the clamps at roughly the same angle that we're going to be using throughout this activity. Then, we want to set up our ramp with our wooden block on top of the ramp with our mass on top of the block. We use the force sensor to slowly pull the mass in the normal direction until it breaks contact with the wood. Then, we want to look at our passcode, and on the slope of the graph, we can see a constant slope, and then eventually it'll spike. Our reading for our data point is going to be the force reading right before the slope spikes, because that's right at the normal force reading.
So today we're working with a passcode force sensor and a friction block to calculate the amount of force that it takes to move it. That's what that looks like. So I'm using a passcode interface on this computer first for time, and so what I'm going to do is click here and then find the maximum, and I enter that maximum into our Excel sheet. Since this piece of wood was not moving and we were maintaining, the force is going to be static friction. In this next activity, we're going to slowly lift up the board until the block starts to at that incline, which is the maximum incline before the block moves, which we'll measure with our ruler and with our protractor. Then take this static frictional force, which is the force mass. In accordance to Newton's first law, force is equal to mass of theta. To mitigate for human error, we're going to do this trial 10 times and then take the average of the degrees, so not the degrees, average of the angle in reverse.
Activity 3, we measure the coefficient of kinetic friction by analyzing a block that slows down and stops due to the friction of. But this time we placed a photo gate that could measure the initial velocity as a block passed through it. Now, when we gave the block a gentle push, it came to rest. And so for each trial, we recorded the initial velocity from the photo gate and measured the stopping distance using a meter. To analyze the data, we use kinematic equation. Final velocity squared equals initial velocity squared plus 2AD. Velocity is 0. We plotted the initial velocity squared versus a distance, and it gave us a straight line whose slope equals. So we repeated this process for multiple trials and compared the result to the constant velocity method.
For activity 1, we tested whether the normal force of an object at rest on an incline is proportional to the cosine of that inclined angle. As predicted by the equation F sub n equals mg cosine theta, using a 200-gram cart, we measured the normal force at several inclined angles and plotted it against cosine theta. The resulting graph shows a clear linear relationship indicating that the normal force varies directly with cosine theta. The slope of the trend line was approximately 2.31 newtons compared to the theoretical 1.96 newtons, giving a percent error of around 18%. Because the data follows the expected trend line, and the slope is close to mg, the results support the theoretical model despite some experimental uncertainty. For activity 2, we measured the coefficient of static friction using two different methods. In the first method, we pulled the block on a horizontal surface until it just began to move, and calculated the static friction constant, mu sub s, from the ratio of the max static friction force to the total weight. Second, we slowly put the board on an incline until the block started sliding down and calculated mu sub s using tangent theta. Repeating the experiment with different masses showed that there is no correlation between the coefficient of static friction and the mass, and both methods gave consistent results, supporting the theoretical model. For activity 3, we measured the coefficient of kinetic friction, mu sub k, using two different methods based on Newton's second law. In the first method, a block was pulled at a constant speed on a horizontal surface, so the net force was 0 and the pulling force was equal to the kinetic friction force. For multiple trials, we calculated an average coefficient of kinetic friction of 0.284 newtons. In the second method, the block was given an initial speed and allowed to slide to a stop. We plotted the speed squared versus distance stopping, and the slope given on the graph gave twice the acceleration. From this, we calculated that mu sub k is equal to 0.28. The percent error between the two methods was approximately 1.6%, showing a strong agreement and supporting the theoretical model. For this lab, we studied normal force, static friction, and kinetic friction and compared our results to theoretical predictions. In activity 1, the normal force versus cosine graph showed a clear linear relationship, which is expected, but the measured slope differed from the theoretical value by about 18%. This was largely due to random error since each data point required estimating when the slope of the Pascal force time graph spiked, reducing precision while preserving the overall trend. The coefficient of static friction was measured using two methods, pulling the block horizontally until it moved and increasing the incline angle until slippage occurred. Both methods gave consistent results, and changing the mass had very little to no effect, confirming that the mu sub s is independent of mass. In activity 3, the coefficient of kinetic friction was measured using two independent approaches. After correcting velocity scaling and photographic data, the two values of mu sub k 1.6%, demonstrating strong consistency with Newton's second law. Overall, despite experimental uncertainties, the results supported the theoretical models described normal force and friction.
We know we use the concept of friction in our everyday lives, but not only that, what if it was gone entirely? That's exactly what to tackle on. Actually, the maglev trains, instead of having those wheel-on roads, they remove kinetic friction entirely and float in magnetic fields. Not only that, but earthquakes. Static friction part to tectonic plates because it's a force that locks fault lines together and then it allows immense stress to build up. Eventually, they do release as earthquakes. But